Sumrat, can you see the recording? Okay, full recording. Okay. So we will today primarily be talking about pause tagging or part of speech tagging, how deep learning helps in part of speech tagging, and what exactly the problem we are dealing with. So in this tutorial, we will be starting with the introduction about the problem statement and what type of data we will be dealing with. Then we will move on to describing how once we have the data set, how can we prepare it for prepare it in a standard format so that we can feed it to a deep learning model so that we get further processing power. Then we will go to the feature extraction. Since the data set is in raw human language, how can we convert it into a machine readable format? Since machines are good mostly with numbers and binary data. Uh, Next, we will move on to how to defining a model in deep learning model. We will primarily be using PyTorch for this session, and we are using a library called PyTorch Lightning for defining the training setup. It is just a wrapper over PyTorch, which will be helpful for abstracting out training and other steps. So we will see that in the later part of the tutorial. Then we will see how simple we get with the training of the model with PyTorch Lightning, and we will see an evaluation. So we will be handling a basic version of a deep learning model and see what level of accuracy we can get with it. Um, so let's move on to the introduction. So first we will be installing so this notebook has been shared in the comment, and you can all simultaneously run the cells on your own and so as to get a feel of what is happening. So firstly we will be installing the PyTorch Lightning package that we will be using for this session. Coming to the theory part of the session, so you have been taught about recurrent neural networks in the classes. So recurrent neural networks are primarily used for handling sequential data, time series data, mostly text also. So texts are a form of sequential data primarily because some parts of the sentences may depend on parts of the sentences that are ahead or after the data. So each word is usually defined by its neighboring context. Hence, we can call it a sequential data. So RNN are very helpful in sequential data where we need an information from previous cell or next cell or so on. So there is usually a hidden unit in the RNN uh, framework wherein the hidden units usually carry forward the information from its previous version. So this is actually a feedback loop like mechanism which can be unfolded in time, and you will get a sense of feeding the same data to the next layer and so on. As the next information comes, you already have the data from the previous state, and it moves on forward. But RNN, when applied to large sequences, say 100 sequence length or so on, we will see that usually when the information is carried forward from very distant parts of the sentences or distant parts of the time series, usually due to the gradient that we are applying, say the sigmoid function and so on, there is a issue with the accumulating gradients over the different hidden units, and over the last part we will see that the gradient due to the first cell vanishes very quickly. So this is known as the vanishing gradient problem, and we will not be able to capture the context of the first cell in the last cell for huge sequences. However, the traditional RNNs are quite easier to implement, and there has been successful attempts in many places. So we will be looking into this. So RNNs have been hugely used in many places in machine translation, pause tagging, and other forms. So there's an advanced version of RNN that we will be using here. We will come to that also. So what is part of speech tagging? So in English, you might have learned that when we are talking about a sentence, there are different parts of the sentence. Like in the sentence, Bob made a book collector happy the other day. So happy is a verb because it describes the emotion. Here book collector is emotion of the book collector. Book collector is the object, so it is also a noun that we will be using. It is a within nouns also there are different forms of nouns. Like when you combine two or three nouns to form a single noun, it's known as a compound noun. Bob here is the subject, which is a single noun, and Bob made. So made is a verb that describes Bob. So here comes the contextualization. So when we were talking about the happy part, so happy comes after both Bob and the book collector. So we are not aware whether to the machine will not be aware whether to map the verb happy to the book collector or whether is it related with Bob or any other nouns in the sentence, or whether it's part of the day. So this is why we are making use of recurrent networks, because we need to capture the context of different parts of the sentence. And this is why part of speech tagging is a challenging problem, because machine needs to understand that which verb is describing which part of the which particular word is describing which other word, and how are they related. So here comes the challenge. So this is a very standard problem in natural language processing, and this actually applies to different languages as well. So within different languages, the order of the subject, verb, object usually changes. Like in Spanish or in English, there is a particular order in which the sentence follows, and this changes from language to language. So that is another difficulty that is faced in this domain, as to how to adapt to different languages while we are creating a part of speech tagging. So in this tutorial, we will be primarily dealing with the English data set only. Coming to LSTM, so as we were describing that within RNNs, usually there is the issue with the vanishing gradient problem for longer networks. LSTM is a advanced version of RNN. It is a gated version actually. So within the hidden cell that we were seeing within the RNN, so there is some advanced mechanism that you can see in this image that is implemented, which are primarily three gates defined: the forget gate, input gate, and output gate, for controlling which data should be passed forward and which data should be controlled to pass forward. So with the use of these three gates, we usually handle the issue of the vanishing gradient problem. You can read more about it in the online blogs and how are they helpful or not. Coming to the dataset, we will be using the Penn Tree Bank, English Penn Tree Bank dataset. This is actually a collection of the Wall Street journals over 1989 to 1992, and this dataset covers over 50,000 sentences, and there are multiple tags related to it. So we will be talking about tokens. So what is tokens? A token, a sentence is divided into multiple word fragments, and each word fragment, so here you can see in the image, as recently as August the company said that, so as recently, and all the words are broken down, and each word we will be calling it as a token. And with each word there is a tag related to it. So this has been manually written down, what is the tag for each sentences. And later on they had developed a program which had a efficient bracketing sequence, which tagged the newer versions of the Penn Tree Bank dataset. But still 50,000 sentences are quite huge for demonstrating in this tutorial. So what we will be doing is that we will be using a subset of the Penn Tree Bank dataset that is available within a library. We will come to that in the data preparation. So this is the detailed list of all the tags that are available within the entry bank dataset. So they have used 36 tags, particularly including modal, adverbs, and so on. This is the complete list of the tags that they have used. Um, okay, coming to the data pre-processing part. Okay, so we will be using the NLTK, the tree bank subset that is already present within the NLTK library. NLTK library, if you're not aware, is a very widely used library for natural language processing tasks. So we will be using the NLTK's tree bank library, tree bank corpus. So it is very easy to download. Just we call nltk.download treebank, and it downloads the subset of the treebank, and we will then import it using nltk.corpus. For pre-processing part, we primarily do here is a splitting of the data set into train, development, and test. That is, so if you are writing for a real world use case, there will be a more rigorous and streamlined use case of the train validation split, and you will be using something like k-fold cross validation or advanced techniques like that. But in this tutorial, we will be dividing it in a standard split of 80-10-10, that is 80% training, 10% development, and 10% testing. So here you can see that we have defined the sizes of the different training tests and development and test sizes, and we have provided those size while using the random split. So Torch utils has a random split function which takes the sizes and splits the data set. The data set is basically the tag sentences from the tree bank. Coming to the feature extraction, what we will be doing is that so in the feature extraction, primarily we will be so when we are providing these sentences to the machines, each sentences can be of different varying lengths. So what we will be doing is that we will be converting all the sentences to a fixed length sentence or fixed length set of tokens, so that machine can always get the fixed size vector for as an input, because varying vector as an input will be creating a problem with the training part. So what we will do is that if a sentence is smaller, we will be using 25 tokens as the sequence length for our tutorial. So if you do a data analysis over the sentences, you will see that within 25 token length, around 96% of the sentences get covered. So 25 token length sentences are being used. If a sentence is less than 25 token, we will be appending a special character known as the pad token. And if the sequence length is greater than 25, pad token is just a special token that says that there is no character for this sentence here. And if the sentence is greater than 25 tokens, we will be basically truncating it. And similarly, we will be doing for the corresponding tags. There will be a mapping of a word to index. So each word in the training corpus will be mapped to a certain index in the word to index mapper, and tag to index will be mapping the tags to a specific index. So in this pre-processing part, we are just extracting those features. So here we can see that we are extracting the sentences tags, then iterating over the sentence. If it is less than sequence length, we append the pads. And if it is greater than sequence length, we just take the first sequence length number of tokens and corresponding tags. Once we have done this, we will be appending this to the word to index and tag to index variables. So word to index and tag to index, word to index is kind of a vocabulary that we are building so that the machine knows that it's a kind of Oxford dictionary for the machine to look up like what all words I have in my dictionary. So once that is done, we will be using our train, development, and test dataset for reprocessing, and this will give us the split form. So train X will contain the corresponding sentence tokens, and train Y will basically have the respective tags that we need to map to. So this is primarily a classification task, if you understand. So you are taking a sentence, converting into a machine readable format, and the machine will tell for each token which which corresponding tag should be attached to this particular token. So if we see the size of the data set, we have 3000 in the training example and around 400 in validation and testing example. So this is primarily a very small subset of the 50,000 sentences available within the original Penn Treebank dataset. So this is primarily to make the tutorial a bit faster. So Somnath will be continuing with the model definition and rest of the part of how to train the code.
Yes, my screen is visible, right?
Yeah, it's visible.
Okay. Okay, so coming to the model class, so here you can see we have defined a post model class. So basically, this class is defined using the PyTorch Lightning module. So these are all the layers that this model consists of. So there is an embedding layer. Now, what this does is that we have a vocabulary. We need to pass the vocabulary size. So embedding layer just creates a numeric format, a vector for each of the index. So for example, if you have 50,000 words in your vocabulary, then for each of these words, there will be a corresponding embedding of size embedding dimension. So this we need to pass as parameter to the model. And so once we obtain the embedding of each word in a sentence, then we pass these numeric embeddings to the LSTM layer. So here we see that we have two parameters, namely num layer and bidirectional, which are passed in this LSTM. So basically, number of layers tells like how many layers of LSTM cells this model consists of, and bidirectional tells whether this LSTM is bidirectional or not. So for example, we saw in the basic RNN model that the input to the hidden state of previous layer was passed to the next layer and so on. Now we can do that from start to end and also from the end to start. So it captures the context both ways. Another thing is that if it is bidirectional, then we add a linear layer above it whose input is 2 times the hidden dimension size. Because if it is a bidirectional, so two outputs will be produced. One will be from front, like from first word for first token to last token, one output for that, and the other LSTM. So it is like saying there are two LSTMs. So the output of this LSTM, its dimension will be batch size times the sequence length times the 2 times hidden dimension. So actually I can write whatever dimensions this consists of. So for example, the embedding dimension, embedding layer, its input will be of batch size times the sequence length and times so basically that is it, batch size comma sequence length, and this is the input tensor, and the numbers will be basically indexes. So here we saw the word to index. So these indexes will be passed as input to this model, and the output of the embedding layer will be basically batch size times sequence length times embedding dimension. So each token would be embedded. Now, similarly, when you go on to the LSTM layer, LSTM its input will be the output of this embedding layer. So that will be batch size from a sequence length times embedding dimension, and it will produce an output which is batch size times sequence length times hidden dimension. If it is not a bidirectional LSTM, else if it is a bidirectional LSTM, then this output dimension will be just 2 times. So that is taken care of. Now each of these inputs is then passed into a linear layer, and so the input dimension is adjusted accordingly. And finally, we have this linear layer basically does the task of classification. So basically, for each token, we need to classify among those tags that we have. So we saw 36 classes. So it does the final linear layer. It will okay. Sorry. The final linear layer, it will help in the classification. Now this is the forward function. So basically, this just calls every layer starting from the input. So this is the input. We call the embedding layer. Then we get the LSTM output. Then we calculate the output of the linear layer and then pass it into the softmax function. So basically, this Lightning module allows us to define this.
Sorry to interrupt. Can you please explain the embedding dimension again?
Okay. So basically, once so you have the raw sentences, like so you have B such sentences, and each sentence is of a fixed length, like 25. We have used 25. Okay. So now we converted this batch size into sequence length. Words into each of these words is now converted into an index using a vocabulary word to index, that was a dictionary. So this will be the input, batch size times sequence length. Now this embedding layer, what it will do is that for each of the token, it will produce a vector or a tensor of this dimension. So this will be like any floating point number. So it will internally, it will have its own weight and all, and it will just produce. So for each token, it is like a lookup. It is like a lookup. Like we have the word to index. Here we defined word to index. So these tokens that we have, these will be passed as input. And then for each of the token, we will obtain a tensor. So it is instead of just passing the index as an input to the model, it is better if we pass some more number of numbers. So it is simply a lookup.
Okay, thank you.
Then, as I was saying, in Lightning model, you have this. We can pass these three functions, that is training, validation, and test. So here this is batch, and this is just a batch index. What it does is that it just simply calls the forward. Then it calculates the loss function and returns the loss. So you can see here the self.loss function. We have defined the loss function as the cross entropy loss. Since it is a classification task, so we have used the cross entropy loss. So just simply we define training step, validation step, test step, and internally this Lightning module will take care of how the data is passed. We'll come to that. And we have used ADAM optimizer. Okay, now coming to training the model. So as you can see here, we have defined some constants. We have defined the embedding dimension for each token to be of size 100. We have defined the hidden dimension, that is the dimension of the output of the LSTM layer, that is also to be 100. We defined number of training epochs to be 10 and batch size to be 4. We can, like, you can vary it and see for other values as well. So now we had this train validation test split earlier. Now we just need to pass it to a data loader. So this is part of the PyTorch library, and we pass the train set. It will divide it into batches of this size, batch size, and it will shuffle the data set basically. So similarly, you can define this validation data set, validation loader, test data set, test loader. And now coming to the model. So as you can see here, we created the model object, and so here we pass the vocabulary size as the size of the dictionary word to index. Similarly, the tag set size, that will be the classification layer output dimension. So that is the number of tags that we need to classify, and the embedding dimension, hidden dimension. So initially we pass the bidirectional flag as false. So we just want a single directional LSTM. This is something called early stopping. So like if the loss function that is used to train the model, if the loss does not change much. So here we have patience 3. So we can think of it as if in 3 epochs the loss is not decreasing much, then stop. We need not train further. And this is actually used this actually monitors the validation loss. And we define a trainer. This is part of PyTorch Lightning library. So we have the maximum number of epochs. We kept it as 10. We're training on the GPU, and we are also passing the early stopping criteria. And then this will just train the model. Trainer.fit. We pass the model, the training data loader, and the validation data loader. So as you can see, this is the training output. So basically, you can see GPU is available. So GPU was used, and so this gives the number of parameters that are used in the complete model. And okay, so this stopped after 8 epochs, and you can see here the test loss was basically 0.41. Now what we do is that we pass this bidirectional as true, and then we again train the new model and test it, like we calculate the test loss. And here so here, as you can see, the number of parameters in LSTM, earlier it was 80.8K, now it is just doubled, since it will produce two outputs bidirectional, and similarly the linear layers dimension is also doubled, I think. Then here this training stopped after 7 epochs, and the test loss decreased 0.38. So you can assume that using a bidirectional LSTM works better in this case. Okay, now we need to report the results, like how good was the classification. So we use the metric of F1 score. So basically here you can see we perform the evaluation on the test dataset, the test loader, and we just compute there is sklearn's classification report where we pass the true tags, true PO stacks and the predicted PO stacks. The output, as you can see, for each of the token, what is the number of correct, what is the percentage of correct classifications, what is the precision, recall, etc. All has been calculated for each of the PO stacks. And also the overall F1 score, here we get it as 91%. Which is actually a good
Can
result.
you explain what does token represent, VB and VV?
Which one here? Okay, these are just the POS tags. Like we saw, right? There were 36 tags. So I am not sure exactly. VB represents verb, I think, verb. VBN something like verb, noun. I am not sure about that. So these are just one of those 36 classes.
Okay.
And okay, so that was the thing. Like we got 91% F1 score using the data set. I think it was 3000 in training and 400 in test. So you can when you run this notebook, you can change these things. You can change the embedding dimension, hidden dimension, the maximum number of epochs.
How many sentences were there?
What?
I mean, in the part of example, how many sentences were there?
Like we showed, right? In training, there were 3000 sentences.
Okay.
Each sentence was converted to sequence length of 25. Sequence length of 25.
And it was done through word to index.
What?
Converting a variable length sentence to a fixed length is done through what?
So this pre-process function you see, right? Inside it, what is it? If the sentence length is less than sequence length, you just append a pad token. This is just a pad. This is just a unique token. And if it is greater than sequence length, then we just take the first sequence length character, first 25 characters. First 25 tokens.
Okay.
Okay, then do you have any more doubts? Like this was it more or less. You can try to pass while defining the model. You can try changing the hidden dimension. You can change the bidirectional flag. You can also add the parameter num layers. There is you can pass it 2, 3, 4, 5, as many as you like. You can check what is the accuracy.
In the model definition, where are you defining the LSTM model?
So this nn.lstm. So this is predefined in PyTorch library, nn.lstm.
Okay, so as we know, LSTM has like 8 sets of parameters for each of the forget gate, input gate, output gate, right? So are those defined in this package only, nn.lstm, or do we have to define it
Yes.
exclusively?
Like the torch library takes care of defining all those parameters.
Okay.
I just had one simple doubt. Uh, Suppose I have a sentence of length 50, so it will break it down into length, fixed length 25 and 25. I think the fixed length was 25, right?
Yes, it's 25.
Yeah. So basically now I need to produce tags for this particular sentence. So I mean, how will it process this? Just to make it clear completely.
I don't get it. We have to make it at fixed length sentence. Like while you are passing it to a model, we are basically passing tensors. So we cannot have arbitrary length tensors. So hence we make it all as a fixed length.
So what you are asking is like if we have longer sentences than 25, how we are processing the rest of the sentence, right? So we will not be, there are two ways to process that, either add a start of sentence and end of sentence marker. But in this tutorial case, we are just excluding the rest of the part of the sentence. To include all the sentences, what you can do is that use the maximum length of the sentence that is available in your data set and set your sequence length to that maximum set. So for all the sentences which are of shorter length, it will append the tag in that case. Or if you are breaking it into multiple sentences, use a start of sentence marker and the end of sentence marker.
So if I use start of sentence marker or end of sentence marker, then I'm not getting it. How will I get the tags? Because I need the next information. For example, the next round of sentence, for example, the 26th word will need the word before that to process the tag. So I'm not exactly
So
getting.
actually, if you want a sentence that has more length than 25, then you have to do during training. You have to make the length to that. Okay, the maximum length should be, let's say, 75. Fine. Else, if you dynamically want to change the sentence length, then you have to use another class called pack parrot sequence. In this message I have shared it. So using this pack parrot sequence, you can handle variable length in LSTM. You can check it.
Okay, in just simple terms, can you just given a sentence, just highlight the processing of the sentence, how the entire sentence is processed to produce the final tag. Please just give a simple general outline. How different parts of the code is actually responsible for processing and finally producing.
Somna show the LSTM image in the diagram, LSTM diagram. In the diagram. No, before this one. So given a sentence, first this x1, in first x1's POS tag will be identified. Fine. Then comes the x2, the word 2, and now the POS tag of word 2 depends on x2 and also the POS tag of x1. So in this way, you generate the POS tags of your sequence length, maximum sequence length.
What you said, QS tags.
The POS tag is parts of speech tag. Whatever your label is, your label of a specific token depends on that token and the label of the previous token.
Yeah, true.
So whatever your sequence length may be, so because in the nm.lstm takes a specific size sequence length, fine. So
Yeah.
if you use this backpadded sequence, it can consider variable length sequence. That is the difference. So in this n.lstm, if you want a variable length sequence, then you have to consider the sentence length with maximum size. Else you have to discard. You have to segregate the sentence.
One more thing. Here I have basically RNN. I have a neuron, and I have an input xi, and at different time steps I'm just cycling. I mean reverting the input back to it.
Yes.
Now whatever the figure on the right is just an unfoldment of the RNN.
Yes.
Now effectively I just have one neuron.
Yes.
And I'm processing it at different time steps. Now the question is, which part of the code reflects this?
That is the LSTM.
I'm saying that
Okay.
I'm
So
trying to draw a map between this and the construction.
okay. So nn.lstm, it will do the whole thing for you. Okay. So in nn.lstm definition, it has what it has taken as parameter, considering as parameter, the embedding dimension. That means what is the dimension of your input? Fine. And this hidden dimension means what is the output dimension, and it has in the forward function is so this in the forward function line number 20. Fine. So embeds equal to self.embedding.x. So what is the dimension of x? Somnath?
X is basically batch times sequence length.
Yes. So this dimension of embedding indicates what is your sequence length, how many times it will iterate. Fine. This sequence length number of times it will iterate. The process will iterate. Fine.
So embedding means I'm actually converting that particular word into a fixed size vector, is it?
Yes.
So the size of that tensor is just the sequence length, is it?
No. So you have batch size.
The length of that tensor is the sequence length. What is the sequence length?
Sequence length is the length of the sentence.
I'm telling you, your input size is the embedding dimension. Fine. Your input size is embedding dimension, and how many time it will iterate, how many input you will take, that indicates by sequence length. So you will take 300 dimension. What is the remaining dimension? 100. So 100 dimensions tensor. How many times? Sequence length number of times. So your neurons input dimension is embedding dimension, and it will take sequence length number of tensors.
Okay.
And this process will parallelly happen in batch size number of times.
Okay.
So you just try to run this code on your own. So and consider check what is the dimension, how these dimensions changing, so that you will understand.
You can insert print statements here, like print x dot set
and check the dimensions.
Can you print any, tags of any given sentence here? I mean, take a sentence.
Okay. So now in the inference, during inference, you can.
Yeah, the inference.
Yeah, we have the So this is the prediction. Control the prediction. This is indexed. I think I can insert a print statement here. And this X, this will be some indexes. Just what
Y hat has the all the softmax probability.
Yeah, this is basically I'm just running in a separate cell.
So I just want to make one thing clear. We are doing word by word embedding of the sentence, right?
Right.
Yes.
In each time step, I'm considering one word as an input, and I'm predicting its level.
I can show you the sentence as well and the tag. It is what to make. Forward.
What?
Y hat dot argmax of -1. How should I interpret this?
So here the model actually will just output the softmax probability. So as you can see, if you go to the model, this linear layer, we have a linear layer, and then it is passed to a softmax function. So it will just return the probability of each token belonging to the one of these tags. So now we need to take the maximum probability, and so in order to do that, we take the argmax, and -1 is basically the dimension over which we get the maximum. So it is the last -1 means it is the last dimension. Okay. So this was the sentence. This has been shown as tags now. Stock index, features, contracts to buy or sell. So as I said, this was some Wall Street Journal text. So this is your sentence. The sentence has been shown as a list. Stock index, future contracts to buy or sell the cash value of a stock index by a certain date. And then it has been padded to make it to 25 length. Yeah, about this internal pad. Some other tokens are also under the plan.
What are these characters J dot and
so actually what happens is that if you have some So I think J Landis Martin, this might be some separate name. J Landis Martin. So it has been broken down into such tokens as per the data set we have. So this was your sentence. Mr. Simmons cut the price. And then you have this the output. I think test loader check it as a batch. Not sure it is not 25. I think this list that you are seeing, this might have 4 sentences in it because the test loader had a batch size of 4. I'm not completely sure, but you can check the corresponding prediction. Like stock index has been classified as noun, future has been classified as NNS, which is also noun, plural noun. I'm not sure about it.
And there is a colon here in one of the tags.
You can go in detail about the exact POS
Colon
tags.
is also considered as a tag here.
It is also a tag. So these are the various classes that we have. IN is preposition.
No, actually, this is not actually perfect because
that's
it
okay.
is not trained.
So this off has been classified as a preposition. A is a determiner. So this is just an example. You can work around with this. Also, I think this sentence might be of 100 length here because it has a batch size of 4. So this has actually 4 sentences in it.
That's why after pad there are some tokens.
After pads there is. Okay, then any other doubt?
Okay, can we check one more inference? Can we check the word? Let's say given a sentence and what is its embedding? Just to check this.
Cannot show. So as I said, in this forward function.
Can we print this embedding of it? Let's say any given word.
So after this embeds, you can put a print and check the embedding.
Yeah.
Let's share the notebook with you. You can try putting all these statements.
You just call this embedding function and you can you can print these embeds and it will.
So after this, you just need to put a print. If you want to print the shape, just put embeds.shape, or if you want to print the embeds, you can simply do print embeds. The problem will be that while you are training it, it will just generate so many outputs, so many things. Just to get an idea, you can put a print statement and just check any one of them.
While calculating the loss, you sort of change the dimensions, I guess, of y hat.
No, this is not changing the dimension. So
This has been flattened out because loss function has a particular dimension in which it takes the input. So all the characters are flattened.
Okay.
-1 basically says that keeping this rest should be means rest of the dimensions except the ones that are.
So y hat is a predicted tax of a particular sentence.
No, it is just softness.
No, it is just the probabilities. So you'll get
it's a probability that this particular word belongs to this tag. Okay. It's a tensor of probability. Fine. Okay. Please upload this in the Teams channel.
Is Devjyoti just
Yeah, you can check in
Just-
the.
Devjyoti upload this link in the comment section of
in
your.
the main chat, yeah, I will do.
Yes, yes, not in chat. There in the comment section.
Yeah, main. Yeah, I will
Oh.
keep that.
In the general. Okay.
Okay, then. Do you have any other doubts?
Okay.
Okay, then.
Mhm.
I think we can
Stop
stop this.
recording.